Okay, so I'm going to introduce our panelists. So first we have Jason O'Sullivan. Jason is a data science manager at Dunnhumby in the category management division. He's a research data science manager, actually, and he has spent the last 15 years working across retail data science. He has a master's degree in statistics and operations research, and his experience spans business model development and productionalization across graphs, NLP, optimization, and deep learning. Then we have Ryan Greenhalgh. Sorry, you can. Okay. I'm French. Okay. So he's the CTO and co-founder at Deep Mirror, a company that is a cloud platform on which life science teams digitalize their R&D workflows to break down silos, learn from their data, and accelerate discoveries in a continuous feedback loop. Then we have Tony Seale. Tony is a knowledge graph engineer. He has spent the last 9 years building enterprise knowledge graph system and graph neural networks in the financial industry. Then finally, last but not least, we have Martin Szummer. He was a research scientist at DeepMind in the past. He has been building machine learning expertise for the last 20 years. He's a machine learning researcher. He has a broad experience working with Microsoft Research, Google, DeepMind, as well as being a startup founder. Okay, so I'll start the panel by asking each one of you, really, what was your experience with distributed representation and graph transformers or transformers in general? Maybe I'll start with you, Martin.
Yes, I guess I have worked more on the research side. So I worked with a lot of graphs which were purely synthetic, and we were essentially developing algorithms for them. So I worked on graphical models, which is a very probabilistic type of graphical model, and I was trying to combine that with graph neural networks to see, can you use graph neural networks to do sort of the classic computations people did on graphical models. Yeah, and I applied different data like click data, also learning the meanings of words, things like that. So using recommenders sort of on graphs to learn these meanings. On transformers, actually, I have watched with excitement how it's developing, but I actually haven't used it myself yet. So that's on my to-do list.
Hey, I'm Ryan. Thanks for the intro. Sorry. Cool talk, first of all, and I think this follows my journey quite nicely of where we came from a company. So we actually started with transformer networks, and a lot of the work we do is try to predict the outcomes of therapeutics. So the RNA vaccine that everybody had during COVID, it's a sequence, it's not a sentence. And what we were trying to do is predict the outcome of these sequences, and you can have different permutations, and they have different biological activities. So we started with transformers to get a representation of them, and then we would try and make predictions of how successful they would be against the target. And then we were like, oh, hold on a minute, sequences or RNA sequences they're not sentences, they fold up in 3 dimensions. And then we were like, oh, this is actually a really good representation for a graph, and it's in its natural form. So then that's when we started using graphs quite heavily, and I think it's been demonstrated quite nicely that with molecules, as well as RNA therapeutics, that they can be really powerful.
Hi, I'm Tony Seale. I work in the finance domain. I started working with building knowledge graphs about sort of 9 years ago. So just doing the typical data crunching that we were doing before, and getting stuck there. And then began experimenting with putting the financial data into a graph. So we're doing a project for a trading desk, amassed all of their data together. They were trading ETFs, but on the rates side. So we basically took the ETFs, which they're like a basket, and you stick bonds in them, and created a graph of that, and then done a whole bunch of interesting predictions over. Once you start feeding in kind of trade data and risk data into that knowledge graph, and then it's kind of expanded out from there.
Cheers. Yeah, so Jason O'Sullivan, I work in the retail data science space, and yeah, Louis, great talk, really enjoyed it. So I guess we started working with graphs kind of quite a long time ago. So yeah, in my role, we were kind of thinking about how we recommend products in different spaces. Graphs make a really nice kind of representation of how those products are interconnected. And when you get into things like bipartite graphs, so where you've got two types of different kind of vertexes and you're kind of connecting each different type of vertex to each other, that's a kind of a really great representation of kind of customers and products, and so that's when you can kind of get into kind of product recommendation and that sort of thing. And then on the transformer side, we've been kind of exploring that kind of recently. We've taken some of the concepts in natural language processing and then applying them to transaction data. And so one of the things that we've kind of been exploring with transformers is around kind of creating embeddings that kind of represent the product. So similar to what Louis was talking about earlier, kind of you want to look for products that are in the same kind of space, same, very close to each other, and that reflects how kind of similar those are from a customer's perspective. So I've been doing that, and then also on the kind of graph neural network side, just been really kind of exploring and kind of playing around, kind of trying to understand how that might kind of expand out kind of some of the capabilities that we already have.
You talk about your work in the past. When you look at things like transformers or graph neural network, how do you decide whether it's worth to dive into it, whether it's better to use a simpler approach or to use a more, let's say, proven approach? So how and when do you decide to dive into such a cutting-edge subject?
So usually, as a researcher, you usually dive into it when that's unknown. So you actually are trying it and you try to find out whether it works. So for me, it would be always. But okay, so for graph type of networks, right, one key thing is that you probably need to have a graph, right, which often you don't have, or maybe there's uncertainty in the graph. So that's the first criteria, right, the structure of the data, right? If it's a graph structure, you probably want to use that type of model. For transformer, I guess the interesting thing is that's, I would say, almost more universal. It seems like if you have sequences or even images, it's quite a universal model, which is unusual because we didn't think in the past, we thought we needed specialized models for all of these things. And this thing is surprising because it seems to apply in many domains. So for that, it seems one should always consider it. I don't think we have worked out how to use it for all types of data. If you have very long sequences, it might be difficult because just it doesn't scale so well. But in general, you probably would want to find a way to use it because it seems to be quite universal.
Yes, on that question, maybe we'll go to you about what you see from the financial industry perspective and the knowledge graph. Precisely, do you have some issues sometime to create the graphs that you would want to operationalize? Is that a simple problem, or is that something that takes a lot of time?
Yeah, I mean, I guess that's the thing about machine learning is that everybody talks about the kind of sexy side of doing the algorithms, but the reality is that most of it is just like horrible crunching of like normalizing your data. So, So yeah, and with a knowledge graph, the first aspect that you have to set up is creating a graph adapter over the top of other sources. So particularly within a financial institution, you can have a lot of traditional databases, relational databases, but you just basically stick a little graph adapter on top of those and turn that into graph data.
So maybe it might be good for you to explain a little bit at a higher level how knowledge graph works, because I didn't cover that during the presentation. Maybe that might benefit a lot of people.
Sure. So a knowledge graph, basically, in a knowledge graph, what you do is you kind of atomize your data down into three facts. So they call it subject, predicate, object. So you sort of take any data, whether it's like a tree in a JSON file or it's a relational database in a table and stuff like that. At the moment, in all of our companies, these data is all siloed and separated off into like kind of different sections. So part one of the game is you stick your graph adapter over the top of that. You do it in a decentralized way, like they call it a data mesh these days. So basically distributed out across the company, get all of your data into a basic graph format, and then create a semantic layer over the top of that. That's stage 2. So first of all, surface the data. Second stage, start to create your semantic ontology, which is hard. The knowledge is in people's heads at the moment, but basically once you've created this kind of semantic layer, so this is stuff in business terms now, then you've got your kind of semantic model. And then you basically stick your graph-shaped neural network into your graph data, which is kind of funneling the information through the it's kind of refracted through the prism of the semantic model. So if you're like a train company, then it's going to be tracks and trains and passengers. In a financial company, we're obviously talking about like trades and risk and clients and counterparties. So these things become things in a semantic model, which then kind of gets mixed in with your AI model, and you're trying to establish this kind of feedback loop going between the two. So you're sending the AI out to discover more and improve the semantics, and the virtuous cycle you're trying to create.
On that question, we talk about self-supervised or semi-supervised techniques during the talk. Is there a way to create this semantic layer in an unsupervised or self-supervised way? Or do you really have to have actual people doing that hard work?
Yeah, you've got to have people. Yeah, sorry. You can have tools to enable them, and it's worth getting up the data first so that you've got something to play with. But yeah, at the end of the day, certainly with this way. I'm just
asking because there was a paper last year called Language Model or Open Knowledge Graph. I don't know if you had a look at this, but they were selling the idea of automatically created knowledge graph. I don't know how feasible it is.
Obviously, like to a certain extent, and this is kind of like the old AI debate, which has raged on, I guess, forever. But like, can you, if you had a large enough language model, is it potentially just going to learn the semantics, and the semantics would be embedded in there? I mean, it's not impossible. Transformers keep surprising people by how much that they can do. But we're not there. We're certainly nowhere near there yet.
Yes, indeed. So, on this question of really usage of graph and the effort involved, what is your experience, Jason, in terms of making those models operationalized at dunnhumby?
So I guess it does depend a bit on how natural a representation it is of your data, I suppose. So in our case, because a lot of what we were looking at was a very, as I kind of mentioned earlier, it was a very natural representation of that data. It wasn't kind of so bad. You certainly do need to kind of consider some of the kind of the practicalities. So obviously, if you've got kind of a gigantic kind of graph with kind of loads and loads of kind of vertexes, then obviously, your edges are going to be kind of some function of that number of vertexes, and the scale of it does become quite a challenge. And I think some of that then becomes a question of, I suppose, from a productionization perspective, like what you need to do on the fly and what you can kind of pre-run, I suppose. So certainly for us, I mean, because the scales of graphs that we're often kind of dealing with aren't kind of massive scale, so we're not kind of talking kind of the scale of data that you see on the internet. It's kind of a lot more kind of practical because you've got products, you've got customers. Like if we were having to deal with the individual transactions, that would be kind of order of magnitude kind of higher. But actually, kind of when we're doing product to products, that's fine. When you're doing products to customers, obviously that scale becomes kind of quite more substantial. So I think it's just, wherever you've got kind of a natural graph representation, it's obviously quite a good way to approach it. But obviously, the other thing I guess you can do, and it's certainly something that we do, though it's more for I guess actually for the quality of outputs, is that we actually, in some cases, we'll strip out kind of a lot of low quality edges. So if some of those edges aren't really that significant, and for the task that we're kind of doing, those don't matter, actually stripping those out kind of allows you to get the kind of the benefit of your data, the benefit of having the graph, but without necessarily kind of having all the computational cost that will be involved in kind of an unconstrained scenario.
I see. Actually, that's a question I was going to ask you, Martin, about what you've done, because you mentioned you've worked with both neural network and probabilistic graphical model, which is something I quite like. Are you a little bit disappointed that those transformers, literally dot product type of model, are working so well when there is no actual probabilistic information encoded into them?
Well, I'm glad there's a new technique out there. Well, I'm very surprised because I didn't think anybody saw this coming, that it would be so useful for many things. But on the other hand, I guess, okay, so the theoreticians, I think they have looked at this for a while and they saw that essentially neural networks are very good at representing different types of computation. So from a theoretical point of view, they can sort of simulate other learning algorithms or learning kind of priors inside them very efficiently. So from a theoretical point of view, it was all, known that it would be possible. But do they have the right inductive priors? I think this is the interesting quiz. Do they learn fast, right? Because often the reason why we had all these specialized algorithms, because they had special knowledge and special structure in them to exploit the data. So maybe one thing I'm disappointed, or I'm hoping people will do in the future, is they will find a way to encode prior knowledge somehow into these transformers to make them maybe more data efficient, so you don't need as much data and maybe also less compute. So that would be an exciting direction, I think. How do you do that?
I think there was a question on this subject. How much redundancy do you think there is in a large language model?
Probably a lot, but yeah, we will have to find ways to make them maybe more efficient. And I think people are working a lot on that. But I think right now, people have tried to do various efficiency tricks, but often you lose some performance. So I don't think we've really nailed it yet.
Also, there is also the line of work around the lottery ticket hypothesis to try to prune those networks, make them smaller, make them run faster. That's also quite interesting. So, Ryan, one question for you. First, can you explain a little bit more in depth to the room what you guys are doing and how does that fit with graph transformers and graph transformer technologies?
So in terms of like the sequences and then going to the graph.
Yes, how you actually do that.
Okay.
Unless that's a secret.
No, I can talk about some of it.
Okay.
So essentially when you have a piece of RNA which is represented as a string or a chemical molecule represented as a string, you can put it through a transformer, like I said before, and come up with a vector representation of that. But if we think about how chemistry works, you pick up a textbook and there's a bunch of rules, which is some subgraph leads to this chemical property. And if we think of the way that graph convolutional networks work, is that you start at a node and then you look at your neighbors and you look at the context, and then you take the information, you update your state, and then you keep doing that deeper and deeper. So what we can actually do is go from these sequence representations to a graph representation, and then start performing graph convolutions, and then the model essentially learns the underlying chemistry of what's going on in kind of a heuristic manner, like you would get with a textbook. So it's learning how the textbook's working, essentially. But to go from these sequences, and I think especially this is maybe where like AlphaFold's relevant, if you think about proteins as well, they can be represented as a sequence, and that's what you would put in as an input into AlphaFold, and then it constructs the 3D representation of this, and the 3D representation is essentially a graph. So then we learn on top of that to come up with a graph embedding of the protein or molecule or piece of RNA, and then we can make predictions about physical properties or biological activity.
Very, very nice. Yeah.
Sorry, excuse my ignorance. I thought a graph is a 2D construct, so you talked about 3D.
Yeah.
You just elaborate on that a little bit, please.
Yeah, so you can put the coordinate information in there. So there's actually some interesting new message passing schemas, which are spherical message passing. So during the training algorithms, you also take into consideration distance between the nodes. And this is actually one of the hardest things that we have, is how do we construct the graph, because we can have 2D, and then what chemical information do we encode? Like, is it one hot encoding of elements, etc.?
Thank you.
So on this question, and actually that's for the panel, what limits do you see in those techniques? I know that there is a classical issue about the quadratic explosion in the transformers. There are quite a few models to try and deal with this, but I'm not sure if those models end up performing better than the traditional, for example, T5 type of model. So what type of limits do you see to those two models?
Yeah, maybe I can start in a graph context here, but the size of the graph is quite important. So as soon as you start going over kind of thousands of nodes, you lose long distance information that might be relevant. So in a lot of drug protein interactions, you have to take a subset of the graph and then look at the problem that way. But the issue with this is the rest of the context might actually have an impact on what's going on. So that's one of the biggest issues for us.
Yeah, over smoothing can be a bit of a problem as well. Like, say you hop out too many places and then it just becomes this kind of amorphous blob. So losing like long distance relationships through the graph and the significance of those, that can be they can be a bit of a problem as well.
I see, because in your context, you're also trying to do multi-hop reasoning, right?
Well, but the kind of the way the message passing work is that the message kind of gets distributed around. So if you then do too many hops within, so you've got too many, usually like the more deep layers that you add, then sort of better things get, but that's not entirely true with graph.
For everyone to understand, can you give an example of, let's say, questions that can be answered with the type of knowledge graph you're building? Is it more distinguishing entities or recognizing entities? Is it more around making inference about the information that has been encoded there? Is it more a retrieval-based approach, or is it more inference-based approach?
Yeah, so most of the stuff that we've done has been around semantic search, so basically just kind of bringing the data, so you've got the data into a knowledge graph. As I say, you kind of tend to have this distributed knowledge graph, but for a particular use case, you'll ingest a bit of that information in, and then they've got their own like kind of set of facts over there, and then they can pump in like natural language questions, stroke plus plus, that are going to be, what's my exposure to, Japanese bombs in the Japanese market, that sort of thing, is then going to go and hit back a question and pull back like the relevant information based upon the facts that they've got in there. So that's the kind of primary stuff. But then also we did a bit of experimental stuff with the ETF desk, where you basically, you can take the bonds, you can take the ETFs, you can then kind of create a graph of bonds that are in the ETFs and the companies that they're related to, and feed through that information to kind of...
That's actually an interesting subject for me, because in a previous life I worked at Market, and we were doing exactly that, but GNN didn't exist yet. Yeah. So did you try the previous methods using things like personalized page rank?
We blew the competition out of the water with that,
Okay, interesting. How about you? What limit or what potential default you see in those methods for your particular use case? Because for you, I guess, metrics become very important as well.
Yeah. I mean, there's probably a handful of points. So some of the points that already raised. So obviously the scale of computing kind of required. So certainly when we're using transformers at the moment, we're having to use GPUs, because kind of trying to do it on a traditional CPU isn't really kind of an option really. And I suppose some of the challenges that we have, though, I suppose it's not so limited to kind of transformers or GNNs, is kind of validation of the results. So, like, I guess it's more a generic problem with the problem space we deal with. But when you're talking about how similar products are, there's no kind of ground truth to assess against. It's kind of quite an arbitrary thing. So you can go do these things, assess these things anecdotally, and obviously there are kind of versions of human annotations, I suppose, that you can use, like what have kind of experts kind of categorized products as. But I think one particular challenge, but as I said, it's not necessarily limited to kind of GNNs and transformers. It's just kind of actually proving out that it's a better result than what you had before. Because I think, I always kind of work on a kind of premise of justifiable complexity. You only want a solution that's as complex as you need it to be. And obviously, if you're in a space where it's harder to validate those, how can you be sure that all of the effort of building kind of that kind of more complex approach is kind of worth the improvement in outcomes?
Okay. Another question for the panel. So we've seen those distributed representation and transformers basically moving from text to images, now to even reinforcement learning, to music and so on. Do you think there is an overemphasis of the research on this particular domain? And do you see other line of research that should be pursued and don't get the credit or don't get the funding that is necessary? Who wants to do?
Sounds like yours for the question.
Well, there have been many bandwagons in machine learning. Like, we had kernel. Well, the first one I remember is kernel machines. Everything was supposed to be kernelized. We had the early days of deep neural networks. Everything was a deep neural network, right? That was, and I guess now we are on graph neural networks, very popular. Transformers, even more perhaps popular. Yeah, I mean, I think it's inevitable that people, when a new thing comes up, there's a lot of interest. So I don't think it's misguided. I think it's very worthwhile to explore as we see the amazing results. I guess one thing, it's always useful to remember other techniques that sort of capture the same things. So for example, for graph neural networks, people may forget that the same or very similar type of computations were done earlier with plain graphical models, where we were doing message passing to spread information through a graphical model. And of course, graphical neural networks, one of the main type of graphical neural network is the message passing neural network, right? So it is, if you look at the equations, they are very similar, but there's a small difference. I don't know if anybody knows what it is, but I'm actually very surprised. I haven't studied, I was looking a little bit in literature to see if people have explored why there's a difference between the old message passing and the new message passing. But I didn't actually find anything, and I was a bit surprised because I'm fairly sure the old message passing is correct. Like, it spreads information in the right way. And the new message passing, I don't think both can be really correct in general. So I'm a bit surprised. I think the new message passing, I guess, is more learned. So maybe it can learn to recover from this difference. But I would be tempted to try to, look at the old things that existed in the past.
You almost said mistake. You are close to mistake.
Yeah, I wouldn't call it a mistake,
Okay.
but
Okay,
definitely interesting difference.
Okay. Yeah.
Oh, sorry, I was just
Go
going to
ahead.
say it's
It's
maybe worth pointing out the geometric deep learning work that's going on there with the blueprints and everything as well, because and you can go to the geometric deep learning website and there's just like tons of great information on there, along with a great framework that you can use, like a PyTorch framework that you can use. But their thesis is to create a kind of blueprint to say that they're attempting to do what was done for geometry in the past, and say that you can kind of abstract out. So really what's happening when you're convolving over an image, you've got a grid shape. So basically you've got a highly symmetrical shape that is within a grid, and that's kind of the inductive priors that is coming into there, is the fact that you've got that shape. So there are other symmetries that can be pumped in potentially, and if we can have a sort of generic enough framework, which is what this is an attempt to do, then if you kind of find the symmetries, it will tune the model a lot better, and could transformers actually be a lot more efficient than they are, as you were saying.
Yes, just to maybe give some background to people who are not familiar with that literature from Michael Bronstein, mostly at Imperial and at Oxford. The approach is almost to consider that every models that have been very successful was a particular case of a larger model coming from pure math almost. I don't know if that's a good characterization, but that's my impression. It's very heavy in terms of the investment needed to understand everything, but those ideas are quite interesting, I have to say. I don't know if they are, well, Michael Bronstein is the head of AI at Twitter, so I suppose he is using it at Twitter, but I haven't seen
and then
industrial
DeepMind.
application.
DeepMind. No, they just did a revamp of the Google Maps, which use that method as well. Yeah.
Sorry, maybe just to add on to what Martin said before about message passing, and this is something that we tend to do as well, is always start with the simplest thing first, and like know why you're doing things, because jumping straight to graph attention networks is kind of a bit of an overkill if you can do the problem using a message passing framework. And then this goes to why you're using graphs in the first place. So pharmaceutical companies have tended to use like XGBoost for doing similar types of problems, but the issue with that is explainability. So like one of the motivations for us is that if we can build a graph model, we can also get explainability of what substructures within the graph are causing the model to do a certain thing. So I think it's like simplicity, and then can you use the underlying model to explain what's going on? Because especially for, drug discovery, or situations where it's really important that you know that if you give a wrong prediction, you're wasting someone's money, you need to be sure about what you're providing. And I think this is another area in terms of like Bayesian inference that should really be put around models. So then you have, you know if your data's in or out of distribution before making the prediction.
Yeah, and I think that comes back to what you mentioned about inductive priors, really. Because depending on the data you have, depending on the problem you're trying to solve, maybe there is a way to find the best inductive priors first, and from those inductive priors, decide on a method that would exploit this. And maybe that will be coming from geometric deep learning, because they are thinking at that level of abstraction, it seems to me. So that's a very interesting line of research. Okay, yeah.
It might be an elephant in the room, but you mentioned graph attention networks, which should be different from GNNs that we saw earlier. And one of the big hammer of self-attention and transformers, it seems, is the positional encoding. So how do you deal with a graph where you don't have a sequence, but you have a more complex structure?
In terms of how we represent the sequence as a graph.
So I guess the question is, are there algorithms or people researching an attention that is really graph specific, that could say, hey, go these kind of links 5 down, and that's where I'm interested, instead of really, a linear graph. Right?
Yeah, I think the closest thing is the work from Peter. Yeah, who has the graph attention convolutions, and I think that's a lot of his work kind of triggered a lot of the attention models in the context of graphs, but we tend to stay away from that because of the added complexity.
Yeah, they're basically paying attention to, so you've got your node there, and then you've got all of the edges which are going out to it, and then in this context, as opposed to it being actually really quite similar, because in this you're taking the sentence, and positional information is obviously important because of that. But in the graph attention network, you've just got a node with a bunch of edges going out to it, and which edge do I pay most attention to the messages coming? So you're just putting a mask onto the message coming in. So it's not position doesn't matter in that context.
And you use fillers to make up for the different numbers for the different degrees that nodes may have.
It's different. But you put those into layers basically. So as you stack it into layers, then the message kind of gets distributed out as you're putting it into the different layers. Which then leads to that problem I was talking about. Eventually it becomes kind of diffused there.
Just one question for Ryan, by curiosity. When the paper, or let's say the news came that DeepMind had managed to create the structure of 200 million protein, what did you feel at that specific moment? Was it desperation or enthusiasm? What was it?
A mix. Maybe I have some controversial views on AlphaFold. So I think being able to predict the structure of all known human proteins is amazing. But then if we think about a disease context, it's normally mistakes in the protein sequence that lead to disease. And this is something that AlphaFold doesn't understand, is how the physics of the folding. It understands based on evolution of what it should look like based on the sequence. But if you have an amino acid that's wrong, you can't predict the structure, and then you still have to do these expensive cryo-electron microscopy images. So I think it's really cool that you can get the proteins and the structure without having to do the experiments of everything. But then if we think about it in the context of disease, I think that would be the next really cool advancement if we understand the physics of the folding with an AI kind of leveraged approach.
Okay. Interesting. Jason, one question for you. So you mentioned what you're doing with transformers and graphs. What type of control do you have against those systems? Are they running in parallel with other type of recommendation, other type of systems that will create other representation of the data or the users in parallel so that you can see what another system would have predicted or would have indicated to you? Or are you more in a phase where you've just updated your stack and moved to those transformers and graph neural networks?
Yeah, very, very much towards the kind of the updating, I suppose, at the moment. So we tend to run everything kind of, I guess, offline for the time being. So kind of as a research kind of data science team, we kind of develop our science, and then we have data science engineers that we work with. In the first stage, will kind of help us kind of productionize that science, and then we have kind of dedicated development teams. So it's worth saying, like, a lot of our science, the way it works, where we're putting it into products that are kind of surfaced in some cases to kind of expert end users. So they might be category experts or that sort of thing. So I guess when we're doing this, there's definitely, we have to go through quite a rigorous kind of evaluation stage. So we work with a lot of different kind of retailers, and so when we're developing a lot of the science, we can't just kind of test and validate on one. We have to kind of test and validate it on kind of multiple ones. So I guess for that reason, at this point, we tend to still kind of evaluate offline, and we're only kind of pushing it kind of online once we're comfortable that it is kind of a sufficient standard. When it comes to some of the kind of the e-commerce kind of .com stuff, there is obviously the ability to do a bit more kind of A/B testing on some of that sort of stuff, but it kind of really depends kind of case by case on kind of the product and the end user as to kind of how much kind of we can kind of, as you say, do parallel testing. Most of it's kind of done still offline, and important that we validate, assess performance, make sure we've kind of ironed out kind of any issues or kind of anything kind of unpredicted as we're going along. And I think back to kind of some of the points earlier, like for us, certainly in a lot of the science we develop, explainability is kind of key. Like we really need models that it's not to be black box and kind of result just pops out doesn't really work. We have to kind of convince kind of the various business stakeholders that it's actually kind of doing the right thing. So definitely when we're thinking about our models and choosing those, that explainability is a key criteria. And so in any situation where because we will get because I say, because the end users will get asked to explain an individual result at times. So like if we make it impossible for us to understand what's going on, then clearly that's not going to put us in a great place. So we definitely have to focus on that explainability side. So
is that a challenge that you, Ryan and Tony, you have as well, being part of highly regulated industries?
Yeah, I mean, yeah, absolutely. So and then there's the whole, there's like ethics programs that are going on and everything. But to what Ryan was picking up, what Ryan is saying, I think the graph gives you an extra edge with, no pun intended, with with explainability, because often you are able how I'd made the decisions. Maybe you could tell me about that thing you were telling me earlier that you did with the explainability.
Yeah, so what we do once we've trained a model is that then we take the labeled data and then we do a Monte Carlo tree search and perturb the graph, and then we look at the outcome of the model, and then we can see what substructures in the graph are basically causing the model to regress to a certain value or to give a certain classification. And then you can look at the frequency of these structures, then you can give clients insights to what it is that's causing the model to predict that, which is super useful, especially for like RNA therapeutics when there's no chemistry textbook for this and people don't really understand it at the moment. But that could be an interesting area of research as well going forwards, because this is really expensive computationally to be able to do that. I think we worked out that it was about $1 a sequence. So, you know, if you've got 100,000 sequences you want to test, it's 100K to find out which substructures. So.
Yeah, we actually had a little tool that we were using when we were testing out some of our stuff, and it would bring up the graph that had sat behind the decision that it would make. So it wouldn't tell you exactly what it was doing there, but you'd be kind of, oh, I've come up with this prediction, and you'd be like, well, explain then, and then we just had a little tool which would bring up the graph and show you the kind of, you know.
Very cool.
Yeah, it was quite cool.
I have to say. So maybe we'll take a few questions from the room before we fold up. Yeah.
So, do we know if any of these representations would lend itself better for quantum computing applications? Or is it a bit of a chicken and egg, like you need the algorithm first?
One thing I can say is that they're optimizing hardware for graph calculations, because obviously they're slightly different from matrix operations, and there's a new set of hardware that's coming out. I forget the names of and that Puma one from. So they're actually now, because the graph stuff's getting more popular, they're now optimizing it down at the chip level. So that's probably going to bring in a whole wave of increased performance. I can't quantum. I can't comment on.
Yeah, I mean, sadly, I think you've got the wrong panelist from Dunhumby for that question. So we have a couple of people working on quantum computing, but I'm not one of them, unfortunately. So.
In terms of NLP, there's a whole range of research from Oxford using molecular category theory to model text, and that would work very well with tensor networks and quantum computers. Look up Bob Coker if you're interested.
Any other question?
So I have a question for Brian. Many years ago, pre-data science, I was an X-ray crystallographer, so it's good to know that you don't think that job is quite dead yet. And I was just wondering, I guess a couple of questions. One is, so in your opinion, AlphaFold doesn't deal with like post-translational modifications like phosphorylation and such. And then secondly, how has AlphaFold, I guess in your opinion, changed drug discovery, if at all?
Yeah. The question, sorry, remind me, there was two there, so I've forgotten.
The first one was about like AlphaFold can't deal with post-translation
Yeah.
modifications like
Yeah.
phosphorylation and such.
Yeah. I remember the answer now. There was a paper that came out in Nature that basically quantified when there was like issues with protein expression, and then AlphaFold like starts struggling to predict the structure. Let's connect and then I can send you the paper. And then the second question was?
In your opinion, has the like AlphaFold really
Yeah,
changed anything to do with
I think it's opened up like loads of value. So there's several companies that I'm aware of, and their kind of underlying offering is just predicting protein structures and then passing them on to other people, or drug interactions with proteins, which definitely wasn't possible before because you would need cryo-EM people, which is painful, I can probably imagine, to resolve the structures. So I think that's had a huge impact. Yeah.
Okay, one last question from the public. Yeah.
Just shout. Come on. Loud voice.
it's kind of domain specific, but I was thinking about the emphasis that was put on starting with a problem that lends itself to graphs, and that's why you start going down this more complex route. But then I was thinking sort of in the finance domain, if I understood correctly, you were describing you've got all these traditional data sources and you make them graphy just to start using graphs. So I was wondering what you got out of approaching it that way.
Yeah, so I guess that's where I diverge slightly from others there, that I think for an organisation of any size, at the moment their data is siloed and broken up into various different places, and that's quite often why I think they struggle to get machine learning projects which are actually going to be impactful to making their bottom line, because they just don't have the volume. They're not a Google, so they don't have, they can't go out and trawl loads of pictures of of cats off of the internet to do their research on. They've got these very domain-specific problems. But on the other side, they've collected, like these bigger ones anyway, have collected a huge, vast array of domain-specific data, but it's fragmented and shattered at the moment. But that's only if you see it as in tabular. So if you change it into a graph, then it's just one massive distributed graph across the whole of the company. And then you can just do your graph-based machine learning on top of that. So I guess I think differently from others there, that my message to anybody that's working in a company now is start getting your knowledge graph project going, because I think personally that is the future, that more and more companies, the name of the game will be, take all of your internal data behind your company firewall, link it all together, start building that semantic model, get your machine learning going on it. In any knowledge-intensive industry, okay, it started in pharma, it's coming into finance now, beginning to go into retail. My view is it's going to go everywhere, so you should just get on with the job and start linking up that data.
I think that's a perfect conclusion. That's a perfect conclusion to the event. Really, thank you very much to you for coming to Data Science Festival, for helping us setting up that event, and we hope to see you in a few months maybe. We have an event actually in November online that you're welcome to attend as well. Thank you very much.
Thank you.